Lecture of today, as I promised last week when I was explaining the extended information filter, that there is a use of this filter in SLAM, and today we're going to see how we can exploit the structure of SLAM to get the efficient implementation for the information filter. Okay, so that's exactly what you try to. The keywords of lecture today is sparse, so we are going to exploit sparsity, and we'll see later on what sparsity can be useful for. It's an extended information filter, so we still need to do some linearization in there. And the other key is for SLAM. So SLAM has a particular structure in terms of conditional independence that we can exploit and leverage for having things efficient. Okay, so a bit of coming back. This is the two main parameterization that we can use to parameterize a Gaussian random variable. We have the moment parameterization, where we have the covariance matrix, and we have the mean of the distribution. And on the other side, we have the canonical representation, where we have information matrix and information vector. Okay? Or some people also call it precision matrix and precision vector, but these are just terminology. And the relations between the two, it's quite straightforward. What the covariance matrix is the inverse of the information matrix, and the mean is given by the information vector multiplied by the inverse of the information matrix, and the same thing on the other side. You can also see this as a set of linear equations, if this helps you as well understanding this. Basically, there is a linear relationship between the information matrix and the mean with respect to the information vector. And to get the mean back, you need to solve the linear system where the mu is the unknown. Okay? That would be when we usually have, probably I can, let's do like this. So nothing gets deleted, and we can still see. Does it get into the, no? Okay. Here, gets in the video. Okay. So basically the system will be like, I have omega mu is equal to xi, no? That's the linear relation between the mean and the information vector. Or if you want to see it in different ways, again, you can see that this is sigma minus 1 mu information vector. No? So this basically says the information vector is the mean, but after you apply the inverse of the covariance matrix or the information matrix, so basically it's saying is the projection of the mean on the information space in some sense. Okay? And these are just the relations. So we will use this relation to derive then the extended information filter from the Kalman filter. So, but before this, let's give an idea why we care about the information form. And the reason is this. Imagine here, I think that's example that I've been doing also before for the Kalman filter. So we have a robot moving around. We have a set of different landmarks, each of these, and all of them are a joint Gaussian distribution. No? So we have here the covariance matrix of the multi-dimensional, multivariate Gaussian distributions, where we have the robot pose and then the location of each of the landmarks. And you see that this is very dense. So here the wider means the less correlated, the darker means more correlated. But you can see that it's a very dark matrix, or at least light gray matrix. Okay? If we now take this matrix here and we invert it, we get something which looks sparse. No? It looks like the values here are very low, and as an initial look, you might think that those are actually all zeros. So you can think of, okay, there's nothing here. They are not related at all in this representation. There is only a bit of relation on the main diagonal, and then there are some relations here and there. Okay? It's not really true. So both matrices are actually dense. But this one, we can say it's numerically less dense in some sense. So those values are actually quite close to 0, and if we zoom in, probably you cannot see it, but all of them are actually very, very small, but not numerically 0. What it means? It means that if you take one row, this is connected to one variable in your multivariate Gaussian, you take another column, and this tells you how much information those two variables have in common. Okay? So it tells you how strongly they are related in some way, but not in terms of if I move one, what happens to the other, but more in terms of what happens if I know the value of one of them. Okay? So the covariance matrix here somehow gives you an idea of marginal correlations, and this one is more an idea of conditional correlation. That's the same duality that we've seen before between the information form, marginalization and conditioning, and the moment form. So this whole thing boils down to the fact that low number influences less, as we all know. So if we use this representation and we try to approximate this very low number and we just put a 0 there, we can have an approximation which is not too drastic. It's not a coarse or very rough approximation, but it's quite close to the real distribution that we're taking care of. But at the same time, since there is a lot of these kind of small numbers, we will have a very efficient algorithm, because with this kind of Kalman filter, information filter family of algorithms, the only computation that are needed to be performed are multiplication between metrics, between vectors, and the information matrix or the covariance matrix are always there to be multiplied. So the less numbers we have here, the more efficient algorithm is. If we know already that there's a lot of zeros, we don't even need to perform the multiplication with the 0. We just need to store only the non-zero elements, and then we go through the vector of non-zero elements and we multiply them. Okay? So it's just a sort of bookkeeping on when the non-zero values are, and then just taking care of them, which basically transform multiplication of this matrix from a quadratic complexity, because we have n square numbers, to a linear complexity in the number of non-zero elements. Okay? Which goes roughly according to which thing you need to consider. If you need to consider just a small subset of this and it's always constant, then you have a constant time update. If you have to consider the whole matrix, but you have something which is roughly linear, no? Because you always have to consider the diagonal here, plus some sparse values outside of it. And if you can keep this number of values constant or bounded, then we have just a linear complexity there. Okay? So that's the main insight in the algorithm. How does it do it in practice? It has an analysis on what first analyzes why these things are 0 and what it means, or why they are not 0. How many of you know what a Markov random field is? Raise hands. Okay, so this here, it's kind of a Markov random field. Okay, so there is a connection between this kind of matrix, so the information matrix, and an underlying graphical structure for conditional independence. So a Markov random field is, we've seen the Bayes network and all these graphical models, no? So they are models where you say, I have a graph, okay? Probably you've seen from AI or different things, where you have an arrow, and then you say A, B, then you might have B to C, and so on. And then you say the joint distribution of these three, so of A give A, B, and C, you can factorize by considering this conditional independence there. Now you can say it's equal to B of A, where we take just the root here, times P of B given A, times P of C given B. No? So basically this tells you how this graphical representation of the independence, conditional independence in this case, reflects the structure of the distribution. Okay? If we have a Gaussian distribution, the interesting thing is that the matrix itself define the graphical structure, and vice versa. How is the case? So we are having a Markov random field, so there is no conditional notion any longer, so there is no directions in the underlying graphical models. And all of these things actually become joined distributions in this case, okay? So this is a way of representing it. And if we now have a Gaussian distribution for each of these variables, basically this ends up that our information matrix will have, now we have 3 variables. We have A and B are connected, so we have something here, something here, something here, something here. B and C are connected, something here, something here, and something here. So whenever there is no direct connection, but they are conditionally independent given, so A and C are now conditionally independent given B, as it was before, and the joint distribution of these 2 variables is actually equal to the product of the 2, no? And this is reflected by the information matrix. So the information matrix is somehow something like the structure of the 0-1 pattern here. It tells you how the adjacency matrix of the Markov random field looks like. And if we now start inputting values, it basically tells you how strong these connections are. So you can imagine that each of these off-diagonal element will tell you how strong these variables are related. No? So you can have this continuum from 0, which means they are unrelated, to very high number, which means they are a lot related, and then you have a slider in between that tells you the lower, the less related they are. No? And this is what basically it's the connection here. We have very strong relations here and here and here, okay? And this, as you can see, it's a relation between the robot pose, that by convention we'll always put it on the top left, and this landmark here, no? Because that's where the connection is. And this is equivalent to a link in this Markov random field between the robot pose and the landmark, which is at this location here, okay? And then we can have some other strong links here. And this is, again, if you look at the row, it's from this landmark here with this landmark here. No? And that's actually the link depicted here on the graph. Okay? So basically, this is telling us that there are some very strong links between the robot pose and some landmarks, which are now these 3 here, which are the landmarks that are directly observed by the robot. No? And then we have some other strong links between some of the landmarks. So some are here, 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 and there. And basically they depict, most probably, but it's not always the case, landmarks that have been observed at the same time by the robot, okay? When he's observing multiple landmarks in the same place. Now, there are some other landmarks which have a very weak relation, very weak dependency, and they might be somewhere around here. And the goal of the sparsification here is to just keep a small number of strong links and ignore the relations among the other landmarks which are weak relations, okay? So it's not really removing it completely, it's let's say transforming it by changing the way the whole distributions are modeled in the information matrix, okay? But we'll see it step by step. So, as I said, you can imagine this information matrix. Yes?
Is the landmark that you have in covariance matrix with respect to the row, but the same landmarks? For example, the second one is because they should be in the same line in case they are the same.
Which one?
The covariance of 2 landmarks.
This one?
Yeah, and that one. Is it the members of this the same as the members that we have with respect to the robot itself, the upper one?
This one? These are different numbers. So this is just, in some way they represent the mutual information between the robot pose and the landmark. Okay, so how much information they have in common. Here you see a block because actually these are 2-dimensional landmarks. Okay, so here the fact that you see this small diagonal in this circle is because there is x and y and x and y in there, no? And the x and y are related with each other. That's the idea. Like the x is more related with the x and the y is more related with the y. That's why you have this part here, and there is a small relation on the xy terms. Here, it's slightly different. It's one more than the other. I don't know why. It might be that somehow the robot is oriented in a particular way where it is only on one x. I'm not sure. But in principle, there are always this block 2 by 2. The numbers are just different numbers. These are just, they come out just because you take a couple of metrics, you multiply with each other, and you end up with this. Okay? It's the usual propagation of the uncertainty and insertion of the measurement update, filter update, and so on. No, so they are just coming up out of that. Does it answer your question?
Yeah, I meant, for example, in case here the link on the right should be the covariance of those features near the robot, exactly, or maybe some other.
This number here?
No, that.
This one?
Yeah.
There's no robot in here.
Yeah, I know, but the landmarks which are detected by the robot this time, or?
So these are some landmarks that have been detected by the robot in the past. Then the robot kept on moving. These are somewhere, and in this case, are in here. No, this case we just imagine as this link. I'm not even sure if there's actually exactly this link. Let me have a look, because there might be any other link. But let's see. This goes down here. No, it should be the same. Because the idea is this, no? You can see this correlates the landmark from this line to the robot pose there, no? Because that's where the triangle ends up. And this one correlates the landmark here with the landmark down there. So if you consider that all landmarks are down there, this is something observed towards the beginning. So it might be that the robot was here at the beginning. And this one, instead, it's much closer. Actually, it's very close to where the robot is. There might even be that the robot just did something like that, or I don't know. But the whole point is, what it matters is the index. This has a ij index in a matrix, or like I plus 1, j plus 1, and so on. It's a 2 by 2 matrix. And this is another index. And if this index match, then it's observed by each other. But so that's not the point here. So the point is just to analyze that there are some relations which are stronger than others, and we want to exploit the weak relations to have more efficiency. So we trade off efficiency with accuracy. Okay? Any other question? Okay. Yes?
Sorry, one more time. The link, the lower one, the link in the graph, isn't it supposed to be bold too, because there's a strong correlation?
Yeah, no, so the boldness of this diagram is just, there is a distinction that we are going to do later on active and passive landmarks, so we're going to get back on this image. And so the bold here just means the one observed by the robot, okay? And all the others are just all the values which are bigger than 0 in this matrix, no? And you can see that even if there's here a lot of white, there is still a lot of connections here. And the reason is because this is actually dense, so each landmark has some values in the link between each other, okay? So I will see later on that we can cut some of them, but we didn't do it yet. So that's the idea. Okay. So, yeah, that's basically, we discussed all this already, and it's just saying that there are basically an interpretation of the graph and the matrix in terms of a Markov random field and associated adjacency matrix. The missing links are conditional independence between the random variables. So basically it says these two variables are conditionally independent given their Markov blanket. So which basically, if you consider only the Markov blanket is the direct neighborhood of a certain node in a graph. So if you take one variable and then you condition it on just the blanket, the one around it, this variable is independent of all the others. Okay, so that's the concept of that. And basically means if there is a 0 in the matrix, there isn't a link in the there is no link in the graph. Therefore, these two variables are conditionally independent. conditioned on the Markov blanket. Again, you can imagine that the values in the off diagonal, so ij, tells us how strong this connection is between the variables. And in case of SLAM, especially if you have a limited field of view, and we'll see what it means later on, a lot of off-diagonal elements are actually 0, okay? And that's because the information that gets propagated from one landmark to another gets weaker and weaker the more the timestamp in which these two landmarks have been observed is far away in time, no? And we'll see how it happens graphically. But basically, the idea of the Seif, or the sparse extended information filter, is to set, in some sense, some of these values to 0, which then makes the matrix sparse and neglects a bit of the mutual information. And once you do that, and you can put a particular structure on the information matrix, you get a very efficient or amortized constant time algorithm for SLAM, okay? And sparse basically means that you have a finite number of non-zero off diagonals independent of the matrix size. So in general, sparse just means there's a lot of zeros, so which means few non-zeros element. For the lecture now, we just assume that when I say sparse, I am assuming a finite number independent of the matrix size. Although cannot always be the case, so you can also sometimes say sparse when it's linear in the number of dimensions instead of quadratic. No? Normally you have n square elements in a matrix. You can say sparse means n, which is the diagonal plus a constant, or you can also just say it's just n, so you can have n elements outside of the diagonal, which gets to 2n in terms of number of elements. But here we just say it's finite, okay? So it's a constant number outside of the diagonal. So what happens during the update of the filter to the information matrix? So let's first see how a measurement update affects it, because that's actually the easiest step for an information filter. And let's have this simple example. I have the robot pose here, and I have 3 landmarks, M1, M2, M3, which are the one here. And here is now just the initialization, so nothing happened so far. The robot is turned on, and the filter is initialized with a certain information on the pose. Okay, so let's say the prior information on where the robot is when it starts. And then it starts observing landmarks. It observes the first landmark, M1, and he updates this part here, and this part here. Okay. Now, why is it the case? It's because he needs to relate the measurement between M1 and X. So this is a pairwise distribution, as we've seen in here. We have, in this case, AB, and we had PAB, okay, the joint distribution of them. And this is updating all these 4. Now, imagine we now observe M2. Any idea which part of the matrix we are going to touch? So we are just going to observe now M2. Are we going to update this element here? Yes, no? How many says yes? 1, 2, 3, 4, 5. Okay, good. Now, are we going to update this element here? Yes, no? Who says yes? 2. Who says no? Nobody? 1? Only 1. Okay. Are we going to update this element here? Yes, yes. 3. Some more? 4. Okay. Are we going to update anything on this line? No? Okay. Who said we're going to update something here? Yeah. Why do you think so?
Because previously we have already have some information about the landmark M1, and adding some new information regarding landmark 2 will also automatically correlate it with M1, I think.
Okay. Anyone else wants to add something on that? Okay. Do you remember how do we do the update? Guys, I have to clean this up, otherwise I'm going to open and close the whiteboard every time. Is it okay? That's like the lecture timing and so on. Okay. So do you remember how we do the update of the information matrix with the information filter? So the update of information matrix in the linear case, it's something like we have omega, then it's equal to the sum of the individual H transpose the information matrix of the observation H. No? And that's this plus that. Okay? So since we have a sum here, the order of the way we put the things together doesn't matter. So the order in which we include information, include observation in our filter has no effect, because I can always change the member of the sum and the result doesn't change. No? I can do A plus B, that's symmetric, so I can do commutative, so I can do A plus B equal B plus A. No? So the order doesn't matter. So in case it's true what you said, that we observed M1 and we need to also update this part here, then it also means that when we observe M1, since we can swap them, we should have updated something here as well, right? No? So you said that we need to put the values here because we already observed M1, and since we are now observing something else, we need to keep track that we observed something before. Okay? And this is the update rule for the information matrix. There is a sum, so there will be M1, something like that depends on M1, plus something that depends on M2. But the order doesn't matter. So in case the order did matter, we should have already everything in here, right?
So only if we observe M1 and M2 at the same time step, then this should be updated, right?
Depends, but depends on how these guys are made. Okay? But so in general, when you have a set of independent observation, which means the H are independent and you can write it like this, that's not the case. In case they are not independent, it means that you have a you cannot write it as a sum of individual components, but you need to write as a big big observation matrix, a big covariance or information matrix here, which also has elements on the off diagonal and so on. Okay, but in principle, this is not the case. We always treat each of these measurements as independent. In reality, you have M1x and M1y in here. They are not independent. They are all related to a single landmark. So that's actually what's happening in here, and that's what's happening in here. Here would be like a x and y, x and y, x and y, and so they're all together. Okay, but in this case, we just assume them to be independent. Okay, to make it the next step, we do only update this part because we only care about the joint distribution between the robot pose, the landmark M2, and how they are mutually correlated. Okay, so which are the mutual information between those two elements. Okay, so during a motion update, basically we just need, during a measurement update, we only have a very quick and very sparse update of this information matrix. No? There is no approximation so far. When we just observe something for the first time, we actually include only the elements in this matrix that affects our observations. And in this case are the one with respect to M1 and M2. And you can see here they are conditionally independent because they are independent given the robot pose. Okay? Now the problem with this approach is what happens when we do a motion update, because the motion update is actually made of two main steps. One step is we just I have only one step there. One step is just we you can see it as adding another variable, which is the pose at the next time, including the relation between the pose of the previous time and the next pose, and then marginalize out the previous pose. Okay? Now you can see it in one step, and this basically can do it on the whiteboard of less steps. We have here, here, then we had, how do you do a star? Like this, and like this, okay? So before we had this, right? Now we have an update, so we're gonna go in this direction, and this is the only information that we have, right? So basically we have, in our matrix form, something that says x times t, then we have x t plus 1, we have m1, and we have m2. And the matrix in terms of conditional independent structure will be, in reality, 1, 2, 3, 4, something like we have t and t plus 1. They are related. Now we have t and m1. They are related. And we have t and m2 who are related. Okay? So that's actually the real structure when we include x at t plus 1. Okay? Now the problem is that we need to marginalize xt out. And if you remember, when we marginalize a variable in the information matrix, what we take is this block minus this block minus this part multiplied by this multiplied by this. If we do it here, what will happen is exactly what you see there. No? So what will happen is that this gets eliminated, so the previous variable gets eliminated, and all the information contained in this, which is the marginal, so the prior on the variable plus the mutual information with the landmarks, gets propagated down here. So we get now some weaker correlation in this part. Okay? And that's exactly what's happening in this case. And if we see it from a graphical point of view, basically it means I'm deleting this. Those two variables, actually, they were conditionally independent, but conditioning on this guy here. This guy is not there any longer, so the information that this guy provides to both needs to be propagated between them, no? Because this is eliminated, this is eliminated. Okay? And the same thing is for this link. This guy had an indirect relation with them by following this path. Okay? And when we are using the information matrix, we don't have a direct, explicit notion here, but we have it through the fact that once we invert this whole matrix, then we get the correlation between them. It's a bit tricky to understand, but if you look at the graphical part, it will make sense. The idea is there was a path between these two variables. I eliminate this variable by marginalizing it. It means I have to recreate the path. And recreate the path means that I need to have something that connects them. And the only way now is directly, because that's the shortest path I can have. And the same thing is for this one here. Okay? So basically, we remove this connection. We remove this connection. We remove this connection. And we end up with the new pose being related to the two landmarks, and also the two landmarks related to each other. Okay? But this relation is weaker than the one that was before when it was a direct relation there. Okay? Therefore, it's a bit grayer than it was before. And the whole concept here is if we iterate over and over with a lot of other landmarks, we're going to end up in a lot of disconnection, but always grayer, grayer, and grayer, until we get almost white. No? And the idea is when it's almost white, we just don't do it and we remove some of them. What we try to convey. So this information comes in here, and we get this very connected information matrix. But we can do a specification step where we basically take this, we check which are the strongest link in terms of mutual information. In this case, we've seen is the one between M1 and M2, and then we have also a strong link between T plus 1 and M2. So what we do is we just decide, okay, that's the lowest element. We want to get rid of this relation here, and we just try to propagate this information through the other links in a way that preserves the information in the best way possible, okay? And we'll see towards the end of the whole package, or the whole class of this lecture here, what it means the best way possible. No? So we don't want to just put a 0 here, but we also want to try to adjust the other numbers so that reflect more what's the inherent distribution behind that, okay? And that's what happened. The link that was here, it's not there any longer, so we can now approximate this distribution by having some, keeping some sparsity here and neglecting some mutual information in there. And again, the effect is to move part of the information which was contained in these two parts, these two off-diagonal elements of the matrix, to the other two off-diagonal elements. Okay? Any questions so far? So, this slide summarizes we come from a distribution like this, where everything is connected, to a distribution like this, where we remove some connections step, we take care of removing these connections and moving a landmark from the active set to the passive set. Okay? These are, in summary, the three main steps. We do a motion update first, we do a measurement update first, and then we do a specification. Do you think these are enough, or do you think we should do something in between that might help us? Do you still remember which was one of the problems of the extended information filter? So it's a nonlinear function. So what do we do normally? We try to compute the Jacobian, right? And what do we need the Jacobian? So what do we need for the Jacobian? Yeah, we need the derivatives, but we also need to compute the derivatives at a certain point, right? And what's this point? What? Sorry? Yeah, it's the mean. And when we see when you've seen the extended, so the information filter, there is no mean propagated. There's always the information vector, no? So to make things easier, instead of solving every time a linear system where we have, where we need to compute the mean every time by just taking the information matrix, inverting it, and multiplying by the information vector, we just keep track of the mean over time, no? So basically then, after the measurement update, we also do an update of the state estimate, no? So we just keep a very short update of the mean with respect to what we have observed so far, no? And we'll see that this is actually, since we have a sparse matrix, we can solve the system of sparse equations. It's a linear system, as you can see in here, so we just need to solve this. And since we have a mean from the previous step, and we just add a rank 1 update or a low rank update of this matrix, we can find a way of computing the new mean quite efficiently by just any sparse solver that we can do. So that's a little bit of more detail, but in principle, we can find the composition of this matrix and update it over time. But basically, what it means is that if we take care of this at every step, we are very efficient because we are very close to the real mean, instead of doing it from scratch at the beginning every time, no? Or whenever we need it. And the last step, again, is sparsification. So, do you want to do a small break, or shall I continue until the end? Which one is for continuing? Okay. Which one is for not? Okay, then I go. So here is again a very pseudocode implementation of the Seif, which says the same thing as the previous slide, just more with elements and what we need. So for doing a motion update, we need the previous mean, the input, the previous information matrix, and the previous information vector. The mean is needed for the linearization part. And we get the predicted mean, which is just the function computed at the previous mean. And we get the predicted information matrix and information vector. When we do the measurement update, again, we need the predicted mean for linearization purposes. We get the predicted information matrix and vector, and we get just the corrected information matrix and vector. The update state estimate just get what we computed so far and give us the new mean. And then we do the approximation in here when we do the sparsification step. I think today we're going to probably see the motion and the measurement update. I'm not sure if we're going to finish with the update of the state estimate and sparsification, but we'll do it next week. So the one thing to take care is that we are not only maintaining the sufficient statistics of the distribution, which is the information vector and information matrix, but for efficiency purposes, we also keep track of the mean of the Gaussian. So it's an over-parameterized way of an over-parameterized filter. So some There is a constraint between these three parameters, but actually it makes sense to keep track of all of them for efficiency reasons. So how does let's go here. Let's see how do we do the motion update. So we need to use one trick, which is something that we should have seen already for the Kalman filter, but if not, we'll just see it again. This is the matrix inversion lemma, or Woodbury inversion lemma. There's a lot of names for this, but they all mean the same. The idea is that if I need to compute an inverse of a matrix, which comes from, which you can write as an original matrix R plus this form here, we can prove that this is equivalent to do the following down there. It seems a lot harder, the things that we see down with respect to the things up, but you need to consider when this is useful. So this is normally useful when this update here is a low rank update. So basically it means that the size of Q as a matrix is way smaller than the size of R. Okay? So basically we are saying if I have something which is very big, you have something which is very small in some sense, in a sense of rank of this update, and we take the inverse, this has a computational cost of the size of R. Okay? But if we write it down in this way, and we assume that we are just updating R and that we already have an inverse of the first part, and we're just trying to find how does the inverse change when we do a small update, we see that this we have it already, so we don't have to compute it. This one we have it already, this we have it. The only thing that we need to invert is this part here, where we actually now are in the dimension of Q. So we move the costly inversion in the dimension of R into a less costly inversion in the dimension of Q and some matrix multiplication. Okay? Now, if all these things is sparse, it's even better because this is actually linear, this is actually linear, and this is constant. So we end up in a linear update. But besides that, we anyway brought something which is almost n cube to something, here was n cube, and here is n square in the worst case. No? So we went down on computational complexity. So I'm not going to prove this, just take it for granted. If you want to get more info on why this is true, you can just go on Wikipedia. That's a nice page on that and how you can actually end up with this equivalence. But for our interest, we just need to know that these things exist and that we will exploit this form for this there. This theorem has been exploited also for the Kalman filter. So the way one derives the Kalman gain is actually exploiting this. And if you look at it carefully, this looks a bit like a Kalman gain up to this part, if you remember the Kalman gain. No? And that's the reason, because these things get exploited over and over for the Kalman filter. Okay? Any question? Okay. Now let's see how we can get the prediction step of the Seif, considering how it comes from the Kalman filter. So we just get the Kalman filter update, and then we'll see how we can derive the Seif update. For the Kalman filter, so keep in mind, we have seen that we have this F matrix, which is an identity and some zeros that is used to either project the state into the small part that only requires the robot, or is to project up the small motion update to the big space state. No? If you remember it from the Kalman filter time, which basically means if we have a mean, and as assuming we have this nonlinear motion model, that's a constant velocity motion model, we say that the new mean is the previous one plus this f times this. And this basically means we are going to just update the part of the state vector mu that is on the top, and that's the one that considers the robot pose. No? And when we do our usual Jacobian for updating the covariance matrix, we get the Jacobian of the motion function, we get this symmetric operation through the matrix F, and we end up to the identity plus this, and this is our G, our Jacobian that multiplies the covariance matrix. Okay? Now, this is what we have here. We can call this R. And actually what we like to do is to use, since we need to compute sigma at -1, we need to invert this thing for the information matrix. No? And this you can just do the same, but we need to somehow consider how we change this expression down here. Now, we have seen from we can just, let's just write now here for simplicity because will help us later on. So the delta, small letter, is just the increment, so the change in the mean. And the capital delta is our Jacobian, just to get notation a bit simpler later on. The idea is that we need to compute omega, which we know is the inverse of sigma. We know that sigma is made in this way, so there is a G, a sigma, which we can also write as omega at -1, and another G, which is then the usual operation here, plus RT, okay? And RT is actually done by Fx, RT, very low dimensional, and Fx. So in principle, we would like to use the inversion lemma on this because we have maybe, let's assume we know now this matrix here. So this one, we have it already. And we can use the inversion lemma because this R is F, low dimensional R, F. Okay? And let's see how we can do it and what happens according to the structure of SLAM. So for now, we just write it that phi is equal to this. So we just, by definition, assume that there is a phi, and this phi is the inverse of this is invertible, okay? And it's actually, it's normally the case because G is composed by an identity matrix plus something that just modifies the upper part of the identity matrix. This is invertible as a Jacobian, we just assume it, which it's normally not always the case in this case, but let's see that it's doable just to help a bit of computation. We can see that basically we want to, so from here, we just say that that's the structure. We'll see what's happening. Now let's take the update. We have it now in a form that we have phi at -1 here, and we have this upper part. So in this case, we can now use the inversion lemma to play, to decompose this inversion into something which is very low dimensional times something that we already have as an inverse. And that's what we assume for now. If we do it, we end up with a 3x3 matrix here that we need to invert, which is a constant time operation because it's always 3x3 if you are in 2D, or it's a 6x6 if you are in 3D. But anyway, always depends only on the size of the robot internal parameters, okay? So it does not depend on the map, it does not grow over time. Then we have this matrix here, which is 0, except for a 3x3 block. And this matrix here, which is also 0, except from a 3x3 block, okay? And then we multiply it by our phi left and right. But in principle, the concept here is that it's constant if phi is sparse. And remember what we meant by sparse before? It's just a finite number of non-zeros outside of diagonal without, that does not grow with the size of the matrix. Or you can say sparse in a more generic terms and bounded in a sense of that the off-diagonal elements are bounded. Okay? If this is the case, then we get the constant complexity. I wanted to write it on the whiteboard because it's probably easier if one sees it. Why is the case? And if we look at so if you write down everything in terms of blocks, we have that our F is actually something like 1, 0, I think. So there is an identity plus a lot of zeros. we have our phi. We can write it as a part that only considers the robot, a part that only considers the landmark, and then we have an off-diagonal part, which is how the robots and the landmarks are actually connected. So that's very schematic way of seeing this. And then we have our R is just R. And let's see what happens when we compute everything there. So we know that when we do F phi ft, this is actually equal to extracting this component of the matrix, okay? Because when we multiply it here on the left, we just get something a vector which has this on the upper part and 0 there and 0 here. When we then multiply by the identity down, we get, it's probably easier if I just write it down here. We have this, and it doesn't matter what's in here, times identity 0. When we do this, we get that the upper part of this vector is actually phi robot 0 and something in here, multiplied by this, which is equal to this by this identity, phi robot, and this by 0. Okay? So basically, when we have an operation like this, it's just as a way of extracting the element in the matrix. Okay? So then it's clear why we have a 3 by 3 matrix. It's just the information of the single robot. And now the question is what happens when we multiply it with F externally. So we know, let's call these things R, let's call R plus phi minus 1 R hat, just to simplify notation. We have now that we have again phi R, phi RL, phi LR, phi L. Let's see what happens if we multiply this by F, where F transpose in this case is identity 0. If we multiply this by that, we have that the first row is actually phi R. Then we get the second row is phi R. Okay. This then multiplies this R hat that we have here. And then we have the same thing on this side. Okay, so that's actually what happens in that multiplication. And basically, we know this is 3 by 3. Okay, this is 3 by 3, and this is 3 by 3. So that's constant. The only thing that we don't know is the size of this. And normally, this part here, phi LR, is the off-diagonal part of our information matrix. If this one is bounded, so if the number of active landmarks is actually constant time every time, then we can say that this whole multiplication is constant, no? Because we have constant here, times constant, times constant, times constant, no? And then we need to take this and sum it up in here, which basically means we have a constant number of elements here. We just need to update the number of elements, the same number of elements here. No? So it doesn't matter. The whole point is that the only thing that gets updated, it's the active landmarks. So whenever we do a motion update, only the information of the active landmarks gets updated, because these are the only ones that are connected with the previous pose directly. That comes from the marginalization. I mean, now I deleted this, but there was these things when one landmark was not directly connected to the robot pose. We go on, we remove one, and then we only connect the things in the active set, but not the one outside of the active set. And these are variables which are in the part which is 0 in this column, and will never get updated when we do this. Does it make sense? Any question on that? Yes? No? maybe? Okay, I mean, it's clear why this is constant, right? We just did it algebraically, and we assume that this is where we put, that's where we put the zeros, okay? So that's where we decide to put zeros and remove some landmarks from the active set to the non-active set, okay? That's where we put the zeros. So we artificially make sure that this one is constant. So the number of non-zero elements in this phi al r is constant. So the thing that connects the actual robot pose with the landmarks. And since we do this, we can see that the number of multiplications that you need to do is constant here. Okay? Does it make sense? Yes, no? If you have a question, just raise hands and I'm going to explain it. It's no problem. Okay. So we can now call these whole things here kappa. That's what I've done on the whiteboard. And we say phi minus kappa is our update. Now, the whole question is that if we can compute phi t efficiently, so if you can do these things here efficiently. And that's actually, yes, we can do that. And let's see how we can do it. So again, if phi is sparse and bounded, as I was saying before, we can still do it in constant time. So if you now look at the structure of G, this is equal to E plus F transpose delta F at minus 1. Okay? Now this is actually equal to this matrix here, which is the identity plus delta and the identity down there. Okay? Because this one just brings our delta up and puts it only in the part which is okay, like the orthogonal. Okay, let's say it puts it here. I don't want to go into projections, orthogonal space, and so on. And the lower part is always 0. Okay, so we just get identity from the sum here. Now we have a block diagonal matrix, and the inverse of a block diagonal matrix is actually the inverse of the respective blocks. Okay, so we then get to this as the inverse filter. And we can again assume that we know the data association. So we know which landmark belongs to which row and column of our information matrix, or which element of our state vector. And again, we do the usual trick that if you've never seen a landmark before, we first directly update the mean vector with the values that we're observing right now. Okay. Otherwise, we are taking our delta, which is the predicted, so the difference between the predicted mean of the landmark that we've already seen that we are updating right now and the one before. And this basically is the residual in some sense. That's the difference between what we predict, which is the mu in that part here. We assume now we have full observation of the landmark, minus what we observe directly from this guy here. Okay? And we use this to know which is, we use it to compute our predicted measurement, which is the square root of the distance. We are considering a range measurement in this case, and the inverse arcotangent and inverse tangent with respect to this delta, minus the angle of the robot, which is the bearing of our landmark. That part here is the same that we have seen for the AKF. It did not change. It's just a step of including unseen landmarks and predicting the observations. Okay. The interesting thing is that we need the mean in this case, no? Because we also need the mean to know which is the predicted observation that we can get. Once we have this, we get our usual Jacobian. We compute the Jacobian matrix in this way, and we can see that we can directly apply all the measurement at once by just summing them in. This is what I've written also before, again deleted. This is the update rule for the information matrix. So you can see that it's just the sum of the Jacobian transpose times the information matrix of your measurement times the information matrix, times the Jacobian. And the order on which you include measurements actually does not matter. And the upper part here, the update of the information vector, is also similar. We basically take our Jacobian. Here we take our, this is the mean, so that's the difference in the prediction. Here you can see that we get this is the projection of the mean into the space. And when we multiply it by q minus 1, this is actually the information vector of your observation. Okay? So this whole multiplication here is basically up to this part. It's basically saying this is the information